Right, welcome to my first ever recorded lesson, and it's going to be called Unit 4, Electrolysis of Aqueous Solutions. How exciting. These are the answers to the homework that you should have done from the previous lesson, and they're in the PowerPoint, which is a separate attachment. Yeah, good. Okay, so this is where we're at. We have done the basis of electrolysis. We've done the electrolysis of molten ionic compounds. Don't know why that's coming out like that. Last lesson we looked at how to extract aluminium using basic electrolysis, and now we're going to look at electrolysis of aqueous solutions. The relevant page and the textbook is also attached for you, and that's what it looks like, and it's not very good, but there you go. And here comes the start. So, electrolysis of aqueous solutions. Most electrolysis that we do is going to be when the ionic compound that we're splitting up using electrolysis is dissolved in water. We're not normally going to do what we've done up to now, which is melt it. We remember to do electrolysis, we need to have ions that are free to move. So the first way that we did this was to melt them, to melt the giant ionic lattice so the ions were free to move. But now we're going to use an alternative way. We're going to dissolve them in water. And when the giant ionic lattice is dissolved in water, the positive and negative ions become free to move. If they're free to move, we've got charged particles that are free to move, so we've got something that can conduct electricity. However, water is a really weird molecule. We know that because it's a non-metal and a non-metal, its bonding is going to be covalent, and as a result we would expect it not to conduct electricity and not to have any ions. Its structure is going to be, its formula is H2O, so its structure is simple molecular, but it does a very strange thing. Well, not all of it does a very strange thing. 1 in 100,000 molecules of water does a very strange thing. So literally 1 in 100,000 will do this. It will turn from being a molecule of H2O, 1 oxygen and 2 hydrogens, and it will ionize to form an H+ ion and an OH- ion. Now, only 1 in 100,000 does this. So if the population of Chelmsford, which is about 350,000 people, were water molecules, only 3.5 people in all of Chelmsford would be able to display this unique characteristic. But it means in any amount of water, in any glass of water, in any beaker of water, there's always a small number of H+ ions and a small number of OH- ions. Good. Which is important when we come to do the electrolysis of aqueous salts, salts that have been dissolved in water. So, in an aqueous solution of copper sulfate, for instance, we've got the following ions present. We've got some Cu2+, obviously, from the copper sulfate. We've got some SO4 2-. Those are sulfate ions, also from the copper sulfate. But because they're dissolved in water, we've also got some H+ ions and some OH- ions. Now that's going to confuse things and complicate things when we do electrolysis. So here's my badly drawn diagram of an electrolysis cell, and I can see that attached to the negative terminal of the cell I've got a negative electrode, and attached to the positive terminal of the cell I've got a positive electrode. The question is, in my solution, which ions are going to be attracted to which? So at the negative electrode I'm going to get positive ions because opposite charges attract. So attracted to the negative electrode I'm going to get Cu2+ ions. But also, because it's in an aqueous solution, I'm going to get H+ ions, those H+ ions coming from the water. Meanwhile, over the positive electrode, I'm going to get negative ions turning up because opposite charges attract. So my negative ions present are SO4 2-, the sulfate ions from copper sulfate, and OH- ions coming from the water. Now, the question is, what's going to happen next? Well, only one positive ion can react, and only one negative ion can react. Why can only one ion at each terminal react? Well, we'll find out about that at A level. It's to do with electrode potentials, but we'll do that in a couple of years' time. Well, you do that, yeah. It's A2, to be honest, year 13. But the important thing is only one positive ion reacts, only one negative ion reacts. The important thing is we've got a choice. With a rule is only one positive ion can react and only one negative ion can react. That's the rule. We've got to find out, we've got to predict what's going to happen. So, predicting which positive ion will react, okay? The rule is this. If the metal is below hydrogen in the reactivity series, the metal ion reacts to form metal atoms. So, here we've got then, there's a reactivity series. There's hydrogen in the reactivity series. And up till now, you're always wondering, well, why is hydrogen in the reactivity series? It's to do with whether it's going to react with acids or not. Well, it is, but it's also to do with whether it's going to react. What's going to react at the negative electrode in electrolysis. And the rule is if the metal is below hydrogen in the reactivity series, the metal ion reacts to form metal atoms at the negative electrode. So we're doing copper sulfate. We can see that copper is below hydrogen in the reactivity series. So this is the reaction we're going to get at the negative electrode. The positive ions are going to be attracted. They're going to gain 2 electrons from the negative electrode, which has got loads of extra electrons. That's why it's negative. And they're going to stop being copper ions and they're going to start being copper atoms. So, we will see copper forming at the negative electrode. We will see brown, coppery, shiny copper metal forming at the negative electrode. Now, what's going on here? Copper ions are gaining electrons, and we know that reduction is gain of electrons. So copper ions are being reduced to copper atoms. Now, I know that's counterintuitive. Reduction means to get smaller, and we're gaining electrons, so that's counterintuitive, but it's to do with oxidation states. We don't need to know about it for another year or so. At the moment, we just need to remember reduction is gain of electrons. That's the first part of my rule then. If the metal is below hydrogen in the reactivity series, the metal ion reacts to form metal atoms. The other half of the rule is if the metal is above hydrogen in the reactivity series, it's the hydrogen ions that react to form hydrogen gas. So, if my metal was above hydrogen in the reactivity series, if, for instance, I was trying to electrolyse zinc sulfate, it wouldn't be the zinc ions that react. It would be the hydrogen ions from water reacting, gaining 2 electrons to form hydrogen gas. So what would I see? Well, at the negative electrode, I'd see bubbles of hydrogen gas forming, and those bubbles would bubble up and they'd be released to the atmosphere. Again, its hydrogen ions are gaining electrons to form hydrogen gas, and this is reduction. So reduction is gain of electrons. So, back to my crudely drawn electrolysis cell. At the negative electrode, I've got 2 ions turning up. I apply my rule. Is copper below hydrogen in the reactivity series? Well, yes, it is. So what I'm going to see is I'm going to see copper metal being produced and forming on the electrode. And if we were at school, we would do this, and you could actually see copper metal forming on your carbon inert electrode. The half equation, as we've already seen, is Cu2+, gains 2 electrons, becomes copper. Question now then is which negative ion will react? We know that only one can, and we know that 2 are turning up, sulfate and hydroxide. Sulfate from copper sulfate, hydroxide from water. In the same way that we had a rule to predict what happened at the negative electrode, we've got a rule to say what will happen for the negative ions at the positive electrode. And the rule, first part, is this. If the negative ion is a halide, i.e. if it's a fluoride, chloride, bromide or iodide ion, then that halide ion will react to form fluorine, chlorine, bromine or iodine. And here is an example of that happening. So here I've got chloride ions, 2Cl-. They will be attracted to the positive electrode. At the positive electrode, they will give up their electrons. They'll have the electrons sucked off them, and those electrons will disappear around the circuit to the negative electrode. And a molecule of chlorine will form. Now, this is slightly different to what's happening at the with the metal ions becoming metal atoms. We remember that metals can exist as atoms on their own, but halogens can't exist as atoms on their own. They immediately form molecules, diatomic molecules, two chlorine atoms joined together. So to have a balanced equation, I need two chloride ions turning up to form one chlorine molecule, giving up two electrons. So if when I do my electrolysis of an aqueous salt, I've got a halide, fluoride, chloride, bromide or iodide, then it's going to be that halide ion reacting to form the elements fluorine, chlorine, bromine or iodine. Now, this process is oxidation because these ions are turning up to the positive electrode, opposite charges attract. They form molecules and they give up two electrons. They are losing the electrons that made them ions. Oxidation is loss of electrons, so what's happening to the chloride ion? It is being oxidized. Excuse me. If the negative ion is anything else, if it's a sulfate, if it's a carbonate, if it's an oxide, if it's anything else at all, okay, it's the OH- ion that's going to react. And the OH- ion is going to react in this unfortunately complicated way. It's going to produce oxygen and water according to this horrible half equation. So let's look at this half equation. 4 hydroxide ions are turning up. Hydroxide ions are negative, so they're going to the positive electrode. They form 2 water molecules, they form oxygen gas, and they give up 4 electrons. There's a mistake in the slide. Brilliant. This should say 4E-. By the time it's uploaded to you, it will say 4E-. We can see that the hydroxide ions are giving up 4 electrons, not 2 electrons, that's a mistake. Oxidation is loss of electrons. So the hydroxide ions are being oxidized. So at the positive electrode, OH- are losing electrons to become oxygen and water. What will we see? Well, we can't see water being formed because the whole thing is taking place in water. So that's happening, but we can't see it. What we'll see are bubbles of oxygen at the positive electrode. And remember, this is 4E-. Okay. Let's change what we're electrolyzing then. Up till now, we've been electrolyzing copper sulfate. Now let's change it to electrolyze NaCl, sodium chloride, or common table salt. So let's think. In an aqueous solution of sodium chloride, what ions have we got? We've got Na+, we've got Cl- from the sodium chloride. The giant ionic lattice will break down to form sodium ions and chloride ions. But also from the water, we're going to have H+ and OH-. Only tiny amounts, because only a tiny amount is produced from water, 1 in 100,000, whatever I said. But nevertheless, they will be there, H+ and OH-. So when I come to consider my 2 electrodes, at the negative electrode, the positive ions will be attracted because opposite charges attract. Na+ will turn up and H+ will turn up. Meanwhile, at the positive electrode, I'll have the negative ions attracted, and we know that they will be the chloride ions from the sodium chloride and the OH- ions from the water. What happens next? Well, I need to apply my rules. Only one positive ion is going to react, and only one negative ion is going to react. Which is which? Well, let's go back to our positive ion rule. Positive ions, if the metal is below hydrogen in the reactivity series, the metal ion will react to form metal ions. So, we need to look at the reactivity series to see where my metal is. And my metal in this case is sodium. There's sodium, and it's way above hydrogen. So it's not below hydrogen, so sodium ions are not going to react. In which case, if the metal is above hydrogen, which it is, it's going to be the hydrogen ion that react to form hydrogen gas. So there we go. Hydrogen ions are going to gain 2 electrons to form hydrogen gas. Reduction is gain of electrons. So, back to my crudely drawn electrolysis cell. At the negative electrode then, it's going to be H plus ions that gain electrons reduced to become H atoms, which then join to become H2 molecules. And we're going to see bubbles of hydrogen at the negative electrode. At the negative electrode, what we're going to observe, we're going to be able to see bubbles of hydrogen. If we collect that hydrogen, we'll be able to test to see if it's hydrogen by doing the squeaky pop test. And here is the half equation for what's happening. 2 hydrogen ions turn up, they gain 2 electrons, and they become hydrogen gas. That's the negative electrode sorted out. The question is now, what negative ion will react? Well, we know we've got chloride and hydroxide turning up. We need to apply our rule to see which will react. And our rule was, if the negative ion is a halide, fluoride, chloride, bromide or iodide, it will be the halide ion reacting to form either fluorine, chlorine, bromine or iodine. And they'll react like this. Now, we've got chloride ions. Well, do we have a negative? Is our negative ion a halide? Yes, it is. Look, it's chloride. So, the chloride ions are going to react to form chlorine gas, giving up 2 electrons. Having electrons taken from them, losing electrons, that's oxidation. I don't need the second part of the rule. The second part of the rule says if the negative ion is anything else, it'll be the hydroxide ion reacting to produce oxygen and water, using that, which is the wrong thing. I still haven't corrected it. So, at the positive electrode, we know we've got chloride ions. Chloride ions are halides, so the chloride ions are going to lose electrons. They're going to become oxidized to become chlorine atoms, which are then immediately going to join to one another to become chlorine molecules. We're going to see bubbles of chlorine at the positive electrode. 2 chloride ions arrive. They have their electrons taken from them. They become chlorine atoms, but immediately they join together to become chlorine molecules, and they give up 2 electrons. Today's consolidation, today's homework then, because it's all homework now, is to look at the different scenarios that I've given you and to consider the negative electrode and the positive electrode for each. You need to work out first of all, which ions are turning up, and then apply the rules to work out which react. So in this first example, which is done for you, the electrolysis of calcium bromide, which is aqueous, okay. At the negative electrode, we know we're going to have calcium 2+ ions from calcium bromide, and we know that we're going to have H+ ions from the water. We are going to apply the rule. We're going to say, well, is calcium above hydrogen in the reactivity series or below hydrogen? If it's above, then hydrogen will react, and if it's below, then the metal will react. Well, calcium's well above hydrogen in the reactivity series, so it's hydrogen that's going to react. Another mistake, it should be 2H+, gains 2 electrons to become a molecule of hydrogen. Meanwhile, we're going to consider the positive electrode. We're going to say, well, which negative ions are going to be turned up? Which negative ions are going to turn up and be attracted? We're going to look and see, well, the negative ion in calcium bromide is Br-, But we also know, because it's an aqueous solution, I'm also going to have hydroxide ions. I'm going to now work out which react. I'm going to apply my rule, and my rule is, if I've got, where's the pointer? If I've got a halide ion, it will be the halide ion that reacts. Well, bromide is a halide, so it's going to react, mistake here, 2 bromides are going to turn up to form bromine atoms, which immediately react to form a bromine molecule, giving up 2 electrons. If I didn't have a halide, it would be the hydroxide ions that react to form 2 waters, an oxygen, giving up 4 electrons. So go through the rest of the sheet and see if you can predict what ions are going to arrive at each electrode, and then which of those 2 ions is going to react. Next lesson, we'll do something else when I've thought about what that is. Thank you very much for listening.